Good morning, one and all. I hope everyone is doing good. Now, I welcome you all for the session 7 of module 3, that is time response of feedback control systems. Now, so far with this module 3, we have completed 6 sessions, and with these 6 sessions, we had one part of the discussion associated with the transient and steady state response analysis of first order system and second order system. And also, we concentrated with the problems based on first order and second order. And the second set of things, what I need to discuss is associated with the steady state error concepts. And this steady state error is associated with the steady state analysis. From the steady state analysis, we learned how to get the expression of C of t for first order system and second order system for unit step response, if you remember. Is it okay? Now, when we have the aspect of obtaining the steady state response, practically speaking, there exists some difference between the practical value and theoretical value, and there will be an amount of there will be an certain error, and those errors are referred to as steady state errors. And in today's class, we shall understand much more details about steady state error analysis. What is steady state error? How do we evaluate the steady state error for a given system? Then what will be the steady state errors for type 0 system, for type 1 system, for type 2 system with respect to distinct inputs via unit step input? Like what will be the errors for unit step input case, for unit ramp input, and even for unit parabolic input, that we shall understand via three different error coefficients: Kp, Kv, and Ka. That is position error coefficient, like velocity error coefficient, and acceleration error coefficient. Okay. And this is one more important aspect.
ಅದು ರಬ್ಬರ್ ಅಲ್ಲ.
Arshita, you need to mute. Is it okay? Now we shall understand these parameters in detail with this session 7. Now first, let me begin with steady state error analysis. Now learning objective is to understand the concepts of steady state errors and its analysis for different types and inputs. Different inputs in the sense, majorly we have 3, actually we have 4, but impulse we won't consider for steady state. Like steady state error, it holds good for 3 inputs, like step input, like parabolic input, and ramp input. And the same thing, it gets varied for different types, like type 0, type 1, type 2, and so on. Now how about the flow of content? First we shall understand the expression for steady state error. Later we shall analyze the steady state errors for type 0, type 1, and type 2 for distinct inputs in terms of unit step, unit ramp, and unit parabolic input. Is it okay? First, let me understand steady state error, which is shortly denoted as ESS. ESS, it stands for steady state error. Now, we shall have feedback control system, which is indicated with respect to this figure. G of S is the open loop transfer function. This is feedback, and overall closed loop transfer function is C of S by R of S. Now, along with this, there is one more signal indicated, that is E of S. E of S is nothing but the actuating signal, or it is also termed as error signal. Is that okay? Now, our agenda is to understand the expression for steady state error. And normally, this E of S is evaluated as such, that is the error signal is evaluated as 1 divided by 1 plus G of S into H of S. R of S is nothing but the input what we shall apply. Is it okay? How do you evaluate this error, steady state? This is error signal. This is not steady state error. This is just error signal, generic error signal. generic error signal from this block is evaluated as 1 divided by 1 plus g of s into h of s into r of s. R of s is nothing but the kind of input what we shall apply. Is it okay? Later, if I concentrate with the steady state error, which is evaluated as this steady state error, ESS is evaluated as such. ESS is equal to limit s tends to 0, s into fs. This is the expression what we shall use in order to evaluate the steady state error. How do we evaluate the steady state error from generic error? That is ESS is equal to limit s tends to 0, s into E of s. Now already we know the value of E of s. Let me substitute with this. Thereby steady state error, it takes the form as ESS is equal to limit s tends to 0, s into E of s. What is E of s? 1 divided by 1 plus g of s into h of s followed by r of s. Actually, this 1 is constant. I can neglect this. Is it okay? Or I shall also consider. Thereby, if I try to have this, if I try to neglect this, limit s tends to 0, s into 1 divided by g of s into h of s into r of s. Is it fine? And this is the expression what we shall use in evaluating the steady state error. Now, next, the steady state error analysis using static error constants is applicable only for 3 inputs: step, ramp and parabolic inputs, as I told you. And the steady state error analysis using dynamic error constants is applicable for 3 arbitrary inputs, that is step input, ramp input and parabolic inputs. And with respect to the analysis, we come across static error constants, 3 static error constants. Those are all Kp, Kv and Ka. Is it okay? When we start analyzing the steady state errors for different inputs like unit step, unit ramp and unit parabola, in such cases we come across 3 static error constants or coefficients. Those are all Kp, Kv and Ka. Kp is applicable for unit step, wherein Kv is applicable for ramp input, and this is applicable for parabolic input. Is it okay? And this Kp is nothing but the static position error constants or coefficient. Where does this Kp comes into picture? This Kp comes into picture with respect to the R of S when it has the value of unit step input, and this Kv comes into picture when R of S has the value of unit step input. And this static acceleration error constant Ka comes into picture when the applied input R of S is parabolic input. Did you get my point? For unit step input, what is the error constants we come across? Kp. For ramp input, like Kv, that is velocity error coefficient. Position error coefficient is for unit step input. Kv is velocity error coefficient is for ramp input, and this acceleration error constants or coefficient is applicable for parabolic input. Is it okay? Kp, Kv and Ka. These 3 parameters from now onwards you need to memorize it clearly. Is it okay? Kp, Kv and Ka. These are all the static error coefficients. This comes into picture when we start evaluating the steady state error ESS for a given system with respect to type and the corresponding input what we shall apply. Is it okay? Now first let me concentrate with the first error coefficient, that is static position error constants or Kp. Is it okay? Kp. Next, as I told you, this Kp comes into picture when the applied input is step input. Thereby, the steady state actuating error signal to a step input is given by E of s is equal to generic expression 1 plus G of s into R of s. What is R of s? R of s is unit step input or step input A into S. Thereby, what is this E of s? It takes the form 1 divided by 1 plus G of s into A of s. Why? Because R of s is A of s. Is it fine? Next, steady state error. What is steady state error? ESS is equal to limit S tends to 0, S into A of s. Later, if I try to substitute limit S tends to 0, S as it is, What is E of S? E of S into 1 divided by 1 plus G of S into H of S, where I may cancel yes and yes. Is it okay? Now what is left out? Left out is A divided by 1 plus y, because 1 is constant. I can't apply limit for this. Thereby I can remodify or I can rewrite this. How do I write this? A divided by 1 plus limit s tends to 0 g of s into h of s. Is it fine? Next I shall define Kp, that is position error constant. The static position error constant Kp, in next step it is defined as Kp is equal to limit s tends to 0 g of s into h of s. Notice this entire thing I can replace it with Kp, that is position error coefficient, which comes into picture when the applied input is step input. Is it okay? Thereby what is the total steady state error? ESS is equal to limit s tends to 0 g of s into h of s. And ESS is A divided by 1 plus Kp. This you need to memorize it clearly. What is Kp? Position error constants, which is given by limit s tends to 0 g of s into h of s. Fine. Next, if I extend the discussion, what the earlier expression what we had was step input. Now this is unit step. Next, if I try to have for unit step input, A is 1, thereby what is the steady state error? It takes the form A badlu 1, thereby 1 divided by 1 plus Kp. Did you get my point? Next, this is the overall steady state error for unit step, and this is for unit step input. Similarly, we had it for step input. Next, we shall understand the nature of the steady state error for type 0, type 1 and type 2 system. Now, how do we bifurcate, or how do we identify as such it is type 0 or type 1 or type 2? In the sense, it is very simple. Now you can observe, this is the transfer function. Now we have this s to the power of 0. Is it okay? When we have s to the power of 0, this is type 0 system. Or in general sense, when we have this s to the power of n, is it okay? N, it can take 0, 1, 2, 3. This s to the power of n, it lies in denominator. This you need to understand it clearly. K divided by, these are all zeros and these are all poles. Is it okay? P1 poles, Z zeros. Is it okay? And with respect to poles, we have this s term, which is of the form s power n. You can have s to the power of small n or capital N, where n can have 0, 1, 2 and so on. When n value is 0, it is type 0. When n value is 1, it is type 1 system. When n value is 2, it is type 2 system. This is how we shall identify the type of the system. Is it okay? Type of the system is decided by the power of s term available in the denominator part of the transfer function. Is it okay? This you should not forget. Now, let me analyze for type 0. Now we understood the steady state error expression for unit step input and step input. Now we shall understand the nature of the steady state error for type 0, type 1. What will be the value? Is it okay? For type 0 system, what is Kp? Kp is equal to, this is limit s tends to 0 g of s. ಇಲ್ಲಿ h of s ಇರುತ್ತೆ. When ಇಲ್ಲಿ h of s ತೋರಿಸಿಲ್ಲ ಅಂದ್ರೆ it is unity feedback. Is it okay? No confusion. Limit s tends to 0 g of s. Next, if I try to have the value of kpss, limit s tends to 0, ಇದು type 0 ಆಗಿರೋದ್ರಿಂದ ಇಲ್ಲಿ s to the power of 0 ಇರಬೇಕಾಗ್ತದೆ. Is it okay? K divided by, these are all zeros and these are all poles. ನೋಡಿ ಇಲ್ಲಿ s to the power of 0 ಆಗಿರೋದ್ರಿಂದ this s to the power of 0 is 1. Is it okay? If I try to apply limit s tends to 0, what does this? It takes the form, this is 0, wherein this is 0, 0 plus 1 is 1. Is it okay? 1 into k is k. This is k divided by 1. Thereby, what is the value of kp? Kp is equal to k for type 0. Thereby, what is this? It results ESS is equal to 1 divided by 1 plus k, which is finite. Is it okay? That is the steady state error or Kp. Is it okay? Or steady state error for step input or unit step input for type 0 system is finite. Similarly, if I go for type 1 and higher systems, okay, type 1 and higher systems. Type 1 in the sense s to the power of 1. Higher systems in the sense s to the power of 2, s to the power of 3 and so on. ಇದು ನೋಡಿ ಅನಲೈಸ್ ಮಾಡಿ ಎಸ್ ಟೆನ್ಸ್ ಟು ಝೀರೋ ಎಸ್ ಟೆನ್ಸ್ ಟು ಝೀರೋ ಆದ ತಕ್ಷಣ ಈ ಟರ್ಮೇ ಝೀರೋ ಆಗ್ಬಿಡುತ್ತೆ. ಹೌದಾ? ಈ ಟರ್ಮ್ ಝೀರೋ ಆದ ತಕ್ಷಣ ಎನಿಥಿಂಗ್ ಡಿವೈಡೆಡ್ ಬೈ ಝೀರೋ ಇಸ್ ಇನ್ಫಿನಿಟಿ. ದರ್ ಬೈ ವಾಟ್ ಇಸ್ ದ ವ್ಯಾಲ್ಯೂ ಆಫ್ ಕೆ ಪಿ ಇಸ್ ಇನ್ಫಿನಿಟಿ. ಇಲ್ಲಿ ಕೆ ಪಿ ಇನ್ಫಿನಿಟಿ ಇತ್ತಾ, ಕೆ ವ್ಯಾಲ್ಯೂ ಕೆ ಅಂತ ರಿಸಲ್ಟ್ ಆಯ್ತು. ಕೆ ಇಸ್ ನಥಿಂಗ್ ಬಟ್ ಫೈನೈಟ್. ದರ್ ಬೈ ಇಲ್ಲಿ ಕೆ ಪೊಸಿಷನ್ ಎರರ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಇಲ್ಲಿ ಫೈನೈಟ್ ಆಗಿರೋದ್ರಿಂದ ಸ್ಟಡಿ ಸ್ಟೇಟ್ ಎರರ್ ಫೈನೈಟ್ ಆಗ್ತದೆ. ಇಲ್ಲಿ ಟೈಪ್ 1 ಏನಾಗ್ತದೆ, ಪೊಸಿಷನ್ ಎರರ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಇನ್ಫಿನಿಟಿ ಆಗಿದೆ, ಸ್ಟಡಿ ಸ್ಟೇಟ್ ಎರರ್ ವ್ಯಾಲ್ಯೂ ಏನಾಗ್ತದೆ 1 divided by 1 plus kp, that is 1 divided by 1 plus infinity, or 1 by infinity, that is 0. Did you get my point? Now we understood steady state error for step input and unit step input. Is it okay? And also the value of kp, that is position error constant. How would the expression for position error constant? Limit s tends to 0 g of s into h of s, that is kp. Now what is the steady state error for step input? A divided by 1 plus kp. For unit step, 1 divided by 1 plus kp. Now what is the value of kp for type 0? It is finite and steady state error is also finite. What is the value of steady state error and kp for type 1 and higher order system? kp is infinite and error is 0 from the mathematical analysis. ಈ ರೀತಿ ನೀವು ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕಾಗ್ತದೆ. Is it okay? Right? This is one set for step input via kp. Similarly, the same criteria to be carried out for kv and ka. Kv for ramp input, ka for parabolic input. Next, I shall move on to into h of s, r of s. Now what is r of s? For ramp signal, a divided by s square. Is it okay? I think I'm audible, right?
Yes, sir.
Yes, sir.
Okay, fine, guys. Now r of s is equal to a divided by a square. Next, if I try to substitute this with this generic expression, limit s tends to 0, s into e of s. Not only e of s differ ಆಗ್ತದೆ. Why? Because r of s is a by a square. Limit s tends to 0, 1 divided by 1 plus g of s into h of s, a divided by s square. I may cancel one s with other s. Now left out is limit s tends to 0, a divided by s into 1 plus g of s into h of s. Thereby, in next step, how do I write this? E of s is equal to a divided by like s plus limit s tends to 0, s into g of s into h of s. Is it okay? I shall multiply s for this. Later, if I try to simplify, what is this? It becomes, now if I try to apply s as 0, this term is 0. Thereby, this I may write it as ESS is equal to a divided by limit s tends to 0, s into g of s into h of s. Thereby, next I may define next error coefficient. Kp was associated with the unit step input. Is it okay? Now this kv is associated with the unit ramp input. Is it okay? And this kv is defined as limit s tends to 0, s into g of s. Is it fine? Thereby, how about the steady state error? ESS is equal to a divided by kv. Why? Because this centered thing is kv. This is for ramp input. How about for unit ramp input? For unit ramp input, this slope or amplitude, it becomes 1. Thereby, ESS is